So now we're going to look at projectiles that are at an angle. So we've been talking about horizontal projectiles, but now let's talk about what happens whenever we shoot these projectiles at an angle. The biggest difference between these two is that the horizontal projectiles, we're going to start from some height and see what happens as they fall. For projectiles at an angle, we're going to start from the ground and see what happens whenever they come back to the ground. So just a reminder about horizontal projectiles is that the x and y are independent. So that holds true for any projectile, horizontal or at an angle. X is always constant, and so in our animation we saw in the last video, we have 5 meters per second, 5 meters per second, 5 meters per second in the horizontal, and it'll be that way for every single one. The vertical velocity starts at 0 up at the top and increases going down. So it's 0, 10 meters per second, 20 meters per second, and 30 meters per second. It increases because of the acceleration due to gravity, which is negative 9.8. So horizontal is constant, vertical is affected by gravity and increases on the way down. So now let's talk about what happens with projectiles at an angle. Well, if an object is thrown at an angle, do we still have a 0 initial vertical velocity? Well, if it's at an angle, then that means that not only is there a horizontal component, but there's also a vertical component. We'll see this in a second. So the answer is no, that there is not an initial vertical velocity of 0 anymore. So the vertical velocity components will follow the same pattern as an object thrown in the air. So if you remember from 1D, whenever an object is thrown into the air in the positive direction, the velocity decreases going up, is 0 at the top, and increases going down. So the initial is not 0. So not 0. The same happens for a projectile that is projected at an angle, is that vertical side is going to decrease on the way up, hit 0 at the top, and then increase on the way back down. The horizontal velocity will stay constant. And so here's another animation that helps to prove this point to you. So we're going to start with the cannon, and you should notice, first let's look at Vx. At every second, the Vx remains constant, including at the very top. So watch when it hits here. It's still 60. So even at the very top, it's 60. Now let's look at the Vy. The Vy starts at 60, decreases on the way up, hits 0 at the top. So we'll watch it again. 60, 50, 40, 30, 20, 10, 0. And then it increases on the way back down again, and it increases in the negative direction. So now the other thing that this one differs than what we're actually going to do in class is that we're going to stop at the same point. This one goes further, but we're going to assume we start from the ground and we hit the ground again. And so whenever it hits here, it'll be negative 60. Okay, so it goes up at positive 60. It'll hit the ground. If this were ground, it would hit the ground at negative 60. You should also notice the shape is a parabola. So I know this looks really complicated, but it's really not. What we're going to do is focus first on the horizontal. So let's look at horizontal first, then we'll look at the vertical, and then we'll see how they interact together. So the horizontal velocities are the green arrows that are right here. And you should notice that all of the horizontal arrows are all the exact same size. And it says here this is the initial horizontal velocity, so V naught x. And here the velocity in the horizontal, Vx, is equal to that initial. Here it's equal to that initial, equal to the initial, equal to the initial. So horizontal is staying constant, does not change. The vertical, on the other hand, starts with this very large initial velocity in the vertical, so v naught y, initial velocity in the vertical, and it gets smaller as it goes up until it reaches the top. And at the top, it's 0. Then, as it comes back down, it goes from 0 to a smaller number, and it gets bigger and bigger until that final velocity, when it hits the ground again, is equal to the negative of the initial velocity. So if this went up at, say, 30, so 30 meters per second, it would be 20, 10, 0. Negative 10, negative 20, negative 30. So start at 30, end at negative 30. The blue arrows are the resultant. That's when you combine both the vertical and the horizontal. And the way we would combine these is by using Pythagorean theorem. And so we would get this arrow going in a much more straight up direction. And then as this vertical is going down, it starts bending more and more towards the horizontal until at the very top, the resultant is the horizontal. And that's because there's no velocity in the vertical. So the resultant is x plus 0, which of course is x. Then as it comes back down, it starts bending more and more towards the vertical. And what you should notice is it creates this perfect parabola. Horizontal projectiles start here and then form a half parabola. For ones that are shot at an angle, since we're assuming ground to ground, we form a full parabola. So X and Y tell us, well, the Y tells us how high it goes. It also tells us the time in the air. The longer it's in the air, the higher it goes. Or you could also say that the higher it goes, the longer it's in the air. Gravity is what affects how long it's in the air. That initial velocity in the vertical plus gravity tell you how long it'll be. The horizontal does not tell you how long it's going to be in the air. Now you might use the horizontal to solve for time, like we did with horizontal projectiles, but what determines the time is that vertical. So my example would be with football, like kickoffs. Whenever you want to actually kick it deep, you're going to kick it way up in the air at a very high angle comparatively because you want it to be in the air for a long time. You want to give your players enough time to run downfield in order to tackle whoever caught it. Now, if you wanted to do an onside kick, the last thing you're going to do is kick it up into the air. You're going to kick it more outward, so more towards the horizontal, a very, very small vertical component. And that's because the lower it goes, then the shorter the amount of time it'll be. So you want it to be very quick time whenever you're doing an onside kick. What the X does tell us is the range. And the range, by definition, is the horizontal distance a projectile will cover. So it's how far down it's going to go. Or down as in outward. So how far downfield. So we're looking at the horizontal distance is your range. And if you think about like when you were talking in history about whenever cannons first became extremely popular in wars and battles and things like that, they were talking about the range of different kinds of cannons, and as technology increased, then you could get further and further range. What they're saying is how far out towards your enemy you could reach with those cannons. So range is horizontal distance. So now let's talk about complementary angles. So do you remember what complementary angles are from math? Well, hopefully you do. They are any two angles that add to 90 degrees. So supplementary are the ones that add to 180, but we care about complementary, which add to 90. So a 30-degree angle has a complement of 60 degrees because 60 plus 30 give you 90. The way this is significant for projectiles is that complementary angles give the same range. So if you were to shoot a projectile at the same speed at a 30-degree angle and a 60-degree angle, they would hit the ground at the exact same spot. But that doesn't tell you anything about the vertical. It just tells you how far out it's going to go. So the question is which angle will give you maximum height? So height is measuring in the vertical, so what angle would get the highest point? It would be straight up. So your answer here would be 90 degrees. 90 degrees gives you maximum height. Anything less than that, it starts going outward as well, and so it gets lower and lower and lower until you reach 0. So which angle will give maximum range? Well, that's what's really interesting, is that the closer your complementary angles are to each other, the further out it'll go. So remember, range is the horizontal distance. So for example, 90 degrees goes straight up. Its complement is 0. So they're both going to hit right where they started. If you go, say, 20 degrees, and, well, let's start with the complement. So 70 degrees. If you go 70 degrees, you're still going pretty much straight up. And so it's not going to go very far out because it's going up too much. So it's not going to hit the ground very, very far away from where it started. Its complement, which is 20, is barely being projected off the ground. And so it's going to hit at a very short distance. Well, those two are very far apart. They're 50 degrees apart. But if we go to, say, 30 and 60, these are larger angles. Well, the 60 is smaller than 70, but the 30 is larger than 20. These are closer together. Whereas 70 and 20 were 50 degrees apart, these are only 30 degrees apart, and they go much further out. These have a much larger range than the 20 and 70 do. So the closer the complementary angles get to each other, the further it goes. So the closest that two angles can get are the same thing. So which angle will give maximum range? It's the one that it's its own complement, which would be 45. 45, 45 make 90. So a 45-degree angle will give maximum range. So closer they are together, the further out it'll go, which means 45 will give maximum range. So you could also look at it now as the closer the angle is to 45, the further out it'll go. So I've got a little short video to show you that shows that. Alright, so in this video he has a launcher very similar to what we have, and he's launching at a 30-degree angle. And he hits the tennis ball over here. So this is at the same height as this projection. So now he's going to shoot it at 60 degrees. And he hits the tennis ball as well. So here's the 30 degrees. Here's the 60 degrees. And what you should notice is they hit at the same spot. Right? They both hit the ground at the exact same, or hit at the exact same spot, equal to where it was launched. But the 30 degree doesn't go as high. And that's because since it's a smaller angle, there's more horizontal velocity than there is vertical velocity. Whereas the 60 degree gets higher because there's more vertical velocity than there is horizontal. This one at 60 degrees will take a longer amount of time to get here. This is what we're talking about, is that the vertical determines time. So the 60, the larger the angle is, the higher it goes, which means the longer it'll take to come back down. The smaller the angle is, then the shorter the height is from your starting point, and the less time it'll take. But complementary angles hit at the exact same spot. Alright, so now let's revisit the x and y again. So what these tell us. So we said that y tells us height and time in the air. And now looking at the video, what we've discussed, we know that larger angles give higher heights, therefore it takes longer for it to come back down. And the total time in the air is called hang time. Hang time, total time in the air. So from ground to ground. Larger angles, higher heights mean longer hang times. The x tells us the range, so how far out it will go. Complementary angles The ones that add to 90 degrees give same range. So 30 and 60 will hit at the same spot. 20 and 70 will hit at the same spot. And the closer they are to 45 degrees, the larger the range. So 45 gives you maximum range. So the closer it is to 45, the larger the range is.